the Professor Goddard with his chair in the Clark College and the countenancing of the Smithsonian Institute does not know the relation of the action to reaction, and of the need to have something better than the vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge laid out daily in the high school. New York Times editorial 1920s. I want to tell you a little bit about Mr. Feynman's big contribution to this story, because Feynman and Schwinger and Tomonaga essentially worked independently. Schwinger was an amazing mathematician, and I still don't understand the math that he was doing. Part of Mr. Feynman's genius was taking something that was very complicated and looking at it in an elegant and different way than anybody else, so that it looked simple. It's very powerful and wonderful skill to have. Mr. Feynman took all of these mathematical calculations and summarized them in a little cartoon, a little picture, which is called a Feynman diagram. So let me try to explain to you the basic idea of the Feynman diagram, because all particle physicists use Feynman diagrams all the time. In fact, it's not just a particle physicist, just about any physicist uses these things, because what they really are is kind of the shorthand for the mathematics that's lying underneath them. Each Feynman diagram is really a symbolic representation of the mathematical equation, and I'll tell you what you do with that equation in a minute. In order to draw a Feynman diagram, you have to have some symbols. So for particles, we're just going to draw straight lines. For example, imagine an electron that's just cruising along, and let me draw the graph of the position on the vertical axis versus time on the horizontal axis. This is a little graph of position versus time, and if the particle is just cruising along, it's a straight line and it's moving forward in time and forward in position. Now, suppose that this photon has a little electromagnetic interaction. The quantum view of the electromagnetic forces is you spontaneously produce a photon. So Mr. Feynman's diagram for a photon is a little wiggly line which leaves the electron and goes running off on their own. That's little spot where the electron and the photons were touching for one brief instant. That was the interaction spot, the vertex where they interacted. Now, why would this happen? It would happen if that the photons were capable of being reabsorbed very quickly, because you have borrowed energy from the vacuum to create that photon. Yes, and you have to give it back. Perhaps there is a proton nearby, and the proton is cruising along and it too interacts with the electron. Then it recoils, because it absorbs something. Even though it's a virtual particle, it recoils. Both particles recoil. That's the force that the electron and the proton feel because of each other. This is a Feynman diagram, and each line, each vertex, each wiggle represents some mathematical operation. The beauty of this is that you don't have to be a brilliant physicist. You could even be a computer and be trained to compute that diagram. Because Mr. Feynman did all the hard thinking for us, and now we have this lovely representation. When you look at that, it almost looks like a little cartoon of the collision between the particles. You can visualize all the nasty mathematics in a lovely, simple way. Oh, this is what René Descartes made the coordinate system, right? So Mr. Feynman did it again. Wow. When you do the calculation, it involves some integrals and some actually more complicated matrix manipulations. And in the end, you get a number. This graph represents a number. What do you do with that number? Well, first you square it, and so that it comes out positive. Yes, that and that number always comes out to be between 0 and 1. It turns out just to work out from the mathematics, and it's a probability. It's a probability that this process occurred. This is quantum mechanics. Quantum mechanics tells you about probabilities of events happening. So if you want to know what is the likelihood that your electron and proton, which came in with some given initial properties and go out with some measured final properties, what's the likelihood that that's going to happen? That's what the Feynman diagram will tell you. You can calculate the likelihood of any event, and that's the best that quantum mechanics can do for you. It's good enough to make these spectacular predictions, right? Now, what about the quantum field theory that I talked about? Well, that photon traveling between the electron and the proton might naively be thought of as the electric field. So there is an electric field between them, and that electric field could split and briefly create an electron and positron pair. You could draw a Feynman diagram for that. At a certain place in the middle, the photon turns into the positron, which is running backwards like this, and an electron which is running forward like so. Then they are annihilated to create a photon again, because they can only fluctuate for a brief moment in the time, and then the photon continue on its way. This is now a modification story. You could calculate this diagram just as you could calculate the first one. It's a numerically harder calculation because it turns out the more vertices you have, the tougher the calculation. Still, a computer or anyone who is trained to interrupt Feynman diagrams could do this. It turns out that the numerical value for this diagram is much smaller than the previous one. That's because there are more vertices, and each time you get a vertex, it introduces a numerical factor that makes the number come out smaller. So this is a low probability event. What about the Lee Normalization trick? It's already built into the mathematics, so you don't have to worry about that infinite sum. The game with Feynman diagram is that you add diagrams, and you add more and more. You can imagine drawing more and more complicated version of this one. Maybe the photon splits twice along the way. Maybe there is 2 photons. You can imagine all sort of complications, but those diagrams always come out smaller. The more complicated the diagram gets, the smaller its value, so you keep calculating until you get tired, okay? That number that I told you for the magnetic strength of the electron was calculated out to some arbitrary level of complexity until the people's computer programming skills sort of petered out, and the computer programming time got to be too long when they got out to 12 digits. But if we get better, faster generation of the computers, we can add one more level of the complexity to the diagram and add another digit or 2 to that calculation. We can keep improving the number. The experimentalists have the really tough job here, which actually is to measure that things. But that's another story. It's a spectacular job to make a measurement of the physical quantity to that level of the accuracy. And, as I said, the agreement is out to 12 decimal places using this kind of Feynman diagram. It's completely universal. If you use this diagram, you can calculate any kind of observable. Remember, what's important is what's coming in and what's going out. You add all possibilities. That's the Feynman rule. You add all possible intermediate diagrams, sum them up, and the answer you get is the numerical estimate that you are interested in. So this is a modern theory of quantum electrodynamics, and it's incredibly powerful. It was developed during the post-war era, the 1950s, and really ties together everything. Now we have a theory that has electricity and magnetism, light, electrons, quantum mechanics, relativity, and fields. It's all been put together. It's truly unified theory of the electricity and magnetism. So now physicists start thinking and asking if they can use this idea to understand all the forces of nature. Electricity and magnetism isn't the only force. What about the strong nuclear force? Could we understand the interaction between proton and neutron and pions using an idea such as this? Mr. Yukawa had proposed that instead of the photon traveling, you had pions traveling. People tried to write down a theory like this one, like a QED, and they failed. They couldn't make it work. Part of the problem was that the interaction was a strong one, so the diagram didn't get smaller and smaller as you added more and more complexity. Another problem was that the particles themselves weren't really the true particle of nature. That is to say, the protons and the neutrons and the pions were themselves complicated objects with an internal structure. We didn't know that in the 1930s or even in the 1950s. That was the underlying simplicity that all those accelerator experiments in the 1950s and 1960s were pointing us toward. It was impossible for us to create a relativistic quantum field theory with the ingredients that we had in the 1930s through the 1950s. Albert Einstein had been working in this era on the unified theory. He was trying to unify all the force of nature, and he failed. He had great successes in his early life and he had some successes in his later life, but he never achieved his true goal. In part, it was simply because he didn't have enough data. He didn't have enough information about what the real building blocks of the nature were. Had he lived another 20 or 30 years, he might have had the tools to complete his work. Who knows? In any case, we now have the ingredients, and where we are going to be heading in the future lectures is first to figure out what are the fundamental particles. Yes. In the case of the Mr. Feynman, he was talking about electrons. Electrons interacting with electrons. Electrons are fundamental particles. There is nothing inside of an electron, as far as we know today, and so that's really why quantum electrodynamics is so successful. Because he was just lucky, I guess, that the fundamental particle he was working with really was a point-like particle. That is an implicit assumption in quantum field theory that the ingredients you are working with are point-like. Yes. This idea of Lee normalization is a critical idea because you are hunting around for a new theory of a new force. You don't have the kind of the strength and background of Mr. Faraday and of all the people who worked to understand electricity and magnetism. You don't have such a deep theory to start with. Instead, you are struggling to find a new theory and with the principle of the Lee normalization. This helps you to say, I am not going to use that theory because it's not Lee normalizable. Some theories are and some theories aren't. When you work it out, sometimes you can make the infinities go away, and sometimes you can't. It's a mathematical fact about theory, so in fact there are very few number of theories you can construct that are inherently Lee normalizable. The theory of the world that we have today to work with, the standard model of particle physics, is a Lee normalizable quantum field theory. It includes the strong force, the weak force, the electromagnetic force, all put together in a theory that's like a QED, but generalized to all the forces that I have been talking about.